I'd like to. The first draft I'm going to collect for the titration report is just going to tell me what you think the acid is, and just the numbers that you got. Okay. And then you'll start writing it up. I'll collect another draft. And so I would say get started on that right away. I was hoping that people would have an assignment like after leaving the computer lab, or before leaving the computer lab. It should be pretty straightforward, at least just to estimate the numbers. But the assignment's not so straightforward, so that's why you got to start with that first. All right, other questions? All right, yeah, there is one more thing I wanted to talk about with kinetics. And that is the formic acid decomposition. So if we look at formic acid, which would also be known as what? What's another name for formic acid? Another name for formic acid is methanoic acid. But methanoic acid can undergo decomposition into CO2 and water, into a liquid. In order for this reaction to accomplish, in order for this reaction to occur, we have to convert this carbon into CO2 and then split that off into some water. And so how does this happen in terms of, is there a unimolecular collision, which slides with the wall and then everything rearranges, or what do you think happens here? Yeah, somehow, this has got to rearrange, right? And without catalyst, this is very slow. In fact, without catalyst, it's a huge barrier to this because we've got to break these bonds here, and then we have to make some new bonds occur here. Actually, is this balanced? No, I didn't balance it there. How can I balance this? Oh, I know why I didn't balance it. I didn't balance because I'm not forming CO2, I'm forming CO, sorry. CO, carbon monoxide, and water. What kind of reaction is this? It's like a redox reaction, but is it? And so let's take a look at the oxidation states here. What's the oxidation state of carbon? Plus 2. Well, oxidation state of carbon in this compound would be here. Take all these, right? So that gives it 2 electrons. Lose these, lose these, lose these. It's supposed to have 4 electrons. Ends up with 2 electrons. So it's 2 electrons short. That's right. Plus 2. Here, this hydrogen. That's 1. This oxygen. This oxygen. And this 2. And this hydrogen. Plus 1. So it does look like a redox reaction, but let's just take a look at the oxidation states here. Well, which one should I assign first? Oxygen. Oxygen gets minus 2. Carbon gets plus 2. Over here, hydrogen, 1 plus 1, and oxygen, minus 2. Was this a redox reaction? No. If it's not a redox reaction, then that leaves us with two choices. What are the two choices? Metathesis or acid-base. What do you think this is? This is, metathesis would be a combination of ions, so we don't really have any ions going on here. And so this is acid-base. This is an acid-base reaction. When you think about it, is this a Bronsted acid-base reaction or a Lewis acid-base reaction? It's a Lewis acid-base reaction. In the Lewis acid-base reaction, we have a base, which is a electron pair of the base. The base should be not acceptor, but electron pair donor, and the acid should be electron pair acceptor. And so this is an example of a Lewis acid-base reaction here, although it certainly doesn't look it, but it is. Now, one of the funny things is this. What are the formal charges here? The formal charges here. Yeah, 1, 2, 3, 4, 5. Oxygen should have 6, so that's plus 1. And carbon is minus 1. Do you notice a conflict? There's a conflict between the formal charge and the oxidation state. Now, what should we do when we have a conflict like this? You know, is the oxygen positively charged or is the oxygen negatively charged? And so which one is more significant in this particular case for dictating? And so the answer is that you shouldn't cross-compare these here. In other words, we compare oxidation states with oxidation states, but we shouldn't compare formal charges with oxidation states directly. But we can, you know, for sure that this thing is charged. The oxygen has a plus charge and the carbon has a minus charge. And that is significant, you know, in the sense that those are real charges. Formal charges are real. Whereas oxidation states are apparent charges, you know, apparent. But these formal charges would be the But you know, these formal charges are going to be biased because oxygen is quite electronegative, so it's going to pull electron density this way. And so the true charge on oxygen, isn't really necessarily given by one or the other. And so this is kind of a weird case, but in terms of the redox, we can see what happens with redox, nothing. Okay? In terms of formal charge, this is important because if you're talking about Lewis acid-base reactions, both of these have a lone pair, you know, the oxygen and the carbon. So which one do you think would be a more reactive Lewis base? The carbon. You know, the carbon has a negative charge on it, has an extra electron, therefore this is going to be a more reactive electron pair donor than this. And so this is how we would use these numbers here in analyzing carbon monoxide. Carbon monoxide turns out to be a powerful Lewis base because of the negative charge on the carbon. This is similar to things like cyanide. Cyanide is an extremely powerful Lewis base. Cyanide also has a carbon with a negative charge due to an extra electron. And so carbon monoxide is a little weird because of the, difference here. All right, now what we're thinking is, when we're thinking about Lewis acid-base reactions, we think about electron pair donor, electron pair acceptor. In Lewis acid-base reactions, the base always does the attacking, just by convention. Obviously, you need an acid and a base to come together, but we always think in terms of the base attacking the acid. Because we always think about the electron pair attacking versus a positive charge. If you think of a positive charge attacking, like an H plus, well, I guess it would be attracted as negative, but it's not always the case. Well, anyway, with catalyst, it'll look different. And so let's take a look at this with catalyst here. Without catalyst, this is an extremely slow reaction, very high activation energy. Now, we add a catalyst. The catalyst could just be acid. And so this is our acid catalyst here. Now, H plus is a Bronsted acid, right? It's also a Lewis acid as well. And so what do you think will attack that acid? You know, out of all these atoms in formic acid, you know, formic acid is an acid, right? And so if formic acid is an acid, why would formic acid attack an acid? An acid plus an acid? Does that make sense? No, it doesn't make sense, but what we have to do is, you know, in general, formic acid is known for its acid properties. But formic acid would also have base properties too. And those base properties are a result of the acid is because of this acidic hydrogen. We call that the acidic hydrogen. We call this the non-acidic hydrogen. Acidic hydrogen, non-acidic hydrogen, right? What about the other atoms in here? As far as the other atoms in here, let's try to evaluate those in terms of a Lewis acid base reactivity. This oxygen, Lewis acid or Lewis base, or neither? This would be a Lewis base, 2 lone pairs, negative charge density, right? This oxygen, base. This carbon's plus 2, meaning it would probably, if it's going to react, it's going to react as a acid, right? But the problem is, if an acid attacks here, then can carbon have an expanded octet? No. So if an acid attacks the carbon here, not an acid, what am I talking about? If a base attacks the carbon here, right, it's a lone pair donor, that means something has to give. You got too many bonds. Can you have 5? All this pentavalent carbon, you can't have 5 bonds, so we got to break this pi bond, knock the electrons out, which is possible. Right? But anyway, what we're looking at here is we have attack. Okay, if there's a collision here, this sp2 can go here, or this sp3 can attack, you know, 1 or 2. And so what you do is, you know, which one happens? Well, both of them happen, right? But which one, you know, even though both of them can happen, one of them might not lead to anything stable. You know, if it leads to something unstable, it's just going to break apart and revert back to where it was before. And so out of these 2 oxygens, which one do you think is potentially more basic, or which one do you think is more likely, 1 or 2? 2?
1.
Yeah. Well, actually either, you know. It's hard to say, isn't it? Because here, if we go to 1, what has to happen is something like this, where this lone pair is converted into a bonding pair, like this. Right? And then this stays the same, this. In this oxygen here, what's the formal charge on it? Yeah. +1. The formal charge is +1. Does that look good? No, it doesn't look so great, maybe. The other option is this. Let's say that this oxygen attacks the hydrogen and forms something like this. On the one hand, this kind of looks like hydronium, doesn't it? This one looks just funny. And then we look, what can happen? Well, what can happen is it could just lose that hydrogen, right? And the hydrogen breaks off, leaves the electrons behind, and we're back to where we started. And so, But what can also happen is something like this. So let's see, we put the proton on here, and then what else can occur? And so, you have to think about that. What can happen here is this. We have H2O here, and if this H2O were to break off, that is, let's say there's some kind of collision. Already this is highly electronegative. Now with a positive charge, it's really going to be pulling on this electron density here. So if there's a collision, it could knock off the water as a species here, water being quite stable. So it can generate water, but what we'd be left with is something that doesn't look so good. Like this. Now this carbon's going to have a positive charge. So we pretty much just move the positive charge from the oxygen to the carbon here. And then this carbon can pull the electron density from the hydrogen. So it takes these electrons. Has to be some other collision. Maybe something plugs off that hydrogen. But carbon still lacks an octet. And so these electrons can drop down here. And we end up with something like this. Plus. So these would be the products. And so rather than having something like, if you were to rearrange the electrons here, how would they rearrange, you know? Somehow these have to pick up this proton over here, pluck that off, and then these electrons have to be pulled behind, etc. And so having an acid catalyst here, although it might not look like it, makes this reaction much more likely to occur. All right. So the reason I wanted to show this is not because I'm going to test you on this particular mechanism, but this is what we were talking about mechanisms, right? Earlier, and how to figure it out. And the way we were looking at mechanisms, we're just colliding two species and then seeing, right, what forms. But how, like when you go on to organic chemistry, or if you go into kinetics more deeply, then not only do you want to think about what types of products might happen, but you also want to look at, what's happening with the orbitals and the electrons in those orbitals. And so, if you go on to organic chemistry, this is all you do. You do this all the time to figure out what the potential products are. Mechanistically, can you get there from reactants to the product? Okay. And so this is just a little introduction to organic chemistry mechanisms. But by knowing mechanisms like this, you can make a lot of predictions about what types of, or what the potential products of the reaction might be, just based on what are likely rearrangements of the electrons. Okay, that was the last part of chapter 14 I wanted to talk about. I want to go on to chapter Mhm.
How could the decomposition of the formic acid be a Lewis-base reaction?
Lewis-acid-base reaction?
Yeah, the formic acid will be both the acid and base because
Yeah.
it's just a decomposition.
Right. It would be both the acid and the base. Like for example, this could potentially happen. Imagine this happening. Imagine that there. Okay, imagine there's this molecule's vibrating, right? And think about if you have an extreme vibration. How does something like this work? Well, if you have an extreme vibration, then this sp2 lone pair can be pushed into this s orbital. And when the sp2 and the s orbitals overlap, it has to kick these electrons out. There's too many electrons, right? And so here, something like this may result. This particular step is called an intramolecular proton transfer. And that is the protons being transferred within the molecule versus an intermolecular proton between one molecule and another. And so these intramolecular proton transfers actually occur. Although, what's the probability of that? Because you got to look, there has to be pretty extreme vibration here to push that orbital in there and knock these electrons out. So eventually it can happen. But what do you form? Well, when you look at this, does this look very good? No, this looks awful because carbon has a negative charge and oxygen has a positive charge. Does that look like a likely scenario? If there's a tug of war for electrons, who should win? All oxygen should win, except for carbon monoxide. Why doesn't carbon monoxide win if there's a tug of war for electrons? Carbon won, oxygen lost. Why? This is something I talked about in Chem 1A briefly. Maybe said one sentence about it. Need Arthur. Anyway, the reason why is because an octet, octet's more important than formal charge. We make the formal charges 0, but we have less than an octet on it, and so that's the reason, or the reasoning given for that. Well, this is going to be highly unstable, so this reverse reaction obviously is more favored. This is making a high energy intermediate. What's the difference between an intermediate and a transition state? Well, a transition state shows bonds being formed and bonds being broken. And so we got bond formation, bond breakage, all in that transition state. After all that bond breakage and bond formation happens, then we got this we call the intermediate product. This can't last very long because it's so unstable. It's got to go to something else. But we wouldn't call this the transition state. The transition state would be something, where this bond's being formed and this bond's being broken. So that would be the transition state. And that transition state costs energy. Whereas this transition state, adding a proton onto this oxygen here, does that cost much energy? No. Are we getting positive and negative? A dipole setup, like this kind of charge separation set up here? No. And so this is way, way more unstable than this. All right, let's take a look at chapter 19 next. chapter 19, we're looking at spontaneous reactions. Spontaneous reactions, you know, these have driving force. That's what makes them occur, and spontaneously. They should occur without any kind of external whatever. And so they just naturally occur. And so what drives a reaction? And so from Chem 1A, what I said here and what I said at the beginning is we want to, the driving force can be summed up in one sentence. What is the driving force? Can you sum it up in one sentence for me? Yeah, we're going from less stable, yeah, to more stable. Well, what makes a species less stable and what makes a species more stable? The bonds. And so normally when we're thinking about driving force, we think about delta H. Remember delta H for a reaction, we could estimate. Delta H for a reaction is just equal to the sum of the delta H for the bonds, the bond energies of the reactants, minus the sum of the bond energies for the product. Normally we think of products minus reactants, but you know, if the bonds in the products are stronger and the bonds in the reactants are weaker, then this number is going to be bigger and it should be exothermic, negative, right? And so this is why it's written this way, exothermic. Exothermic is good, right? And so that means that all exothermic reactions should be spontaneous. And endothermic reactions should be non-spontaneous. Exo should be spontaneous. Endo, non-spontaneous. But unfortunately, this is violated. This rule, and this is just a rule. It's not even a law. You know, what do we have? You know, in the scientific method, we start off with observations, and then you look for patterns, right? And then if the patterns are pretty consistent or pretty good, then we could call it a law. But this pattern isn't so good, and it isn't so consistent, so we wouldn't even call it a law. You know, this would just be some. If you called it a law, you'd have to list a lot of exceptions. And so, in Chem 1A we could look at select reactions. We don't have to look at all the reactions. We can look at reactions that work quite well. In general, this is good, you know, but rule, not law. And so we need something better than that, you know. What's better than that? A law and a hypothesis and a theory, right? And that's going to take more observations. And so, based on observations, this is based on more comprehensive observations. It appears there are two driving forces in nature. Sometimes these conflict, sometimes they work together. So I'll just say sometimes conflicting. And the two driving forces are just these. One, minimize energy. Is enthalpy energy? Nature wants to minimize energy, so do we minimize delta U or delta H? Delta U? Delta U is what? Internal energy. Delta H is what? Huh? Disorder? No, not disorder. What's the difference between delta H and delta U? So yeah, we want to minimize delta U. So delta U, going down. Actually, I shouldn't say. I should say we want to minimize internal energy. Internal energy is also called the total energy, or minimize the enthalpy. And or minimize enthalpy. And so go review these. I think these are Chem 1A. So delta H, exothermic is good. We're minimizing energy. In other words, we're lowering the energy. This. Right. And anyway, H, if you recall, is just U with special restrictions, isn't it? In a way. A little bit more complicated than that, but it's okay. All right. The other one is we want to maximize entropy. This is the entropy is a disorder in the system. Not just the system, but everything. We want to maximize entropy. Entropy is given the symbol S, so we want S to increase. And so when we think about it, if you think about a solid crystal, what's the order, in a solid? Solids have lower or higher entropy than liquids? Lower. Liquids are going to be more disordered. And so the entropy of a solid is lower than the entropy of a liquid. And then the entropy of a gas is higher than a liquid, yeah. And so gases should have the highest entropy. So let's just look at some reactions and then see if we can determine what's happening with delta S and delta H, just qualitatively. And so let's go back. You just do some from your homework. Let's do 5A, carbon tetrachloride. Liquid goes to carbon tetrachloride gas. Delta H, is enthalpy going up or going down? In other words, is energy going up or down? Up. And so this should be endothermic. Right? To vaporize a liquid is going to cost you energy. What about delta S? Delta S is going up too. So we call this delta S going up is good. That's driving force, but delta H going up is not good. And so this is not driving force, right? And so one says no, go. The other says go. No, go. Go. So what do we do? There's a question mark there because we don't know which one is stronger. So let's go to 5B.
So there is no answer?
Huh?
We have no answers?
We have no answer yet.
Yeah.
Yet.
Quick question, what's number 5 say? It's CCl4 going to...
Liquid going to CCl4 gas. All right. Let's go to the next one. Copper sulfate trihydrate, solid, plus 2H2O gas yields copper sulfate pentahydrate, or 5-hydrate, solid. All right, first, let's look at delta H. What do you think is happening with delta H there? Delta H is going up or down? Well, reverse this reaction. If we reverse this reaction, delta H be going up or down? If we reverse this, I would say delta H is going up because we have to break 2 waters. In other words, probably these waters are going to be complex with the copper. And so if the water, or even if they aren't complex with the copper, the waters are stuck in the crystal. What sticks them in the crystal? Ion dipole attractions. And so to knock the 2 waters out costs energy. And so if I want to knock 2 waters off the surface of liquid water and put them in the gas phase, that's going to cost me energy, isn't it? And so we have this rule of thumb. This is a good rule. Bond breakage is endothermic. Bond formation is exothermic. And so when we form bonds, it should be exothermic. When we break bonds, it should be endothermic. Well, in the forward direction, what are we doing? Are we forming bonds or breaking bonds? We're forming. It could be intermolecular forces. I can just replace bonds with intermolecular forces. Same thing. And so delta H should be, this should be good, right?
Don't we break bonds?
In exothermic, we're going from something less stable to something more stable. And so, in that case, going from gaseous water molecules to waters trapped in the solid would be more stable. Yeah. And so this says driving force, right? What about entropy? What's happening with entropy? Entropy is going down because, we're taking this gas now that was randomly, the gas is going to be more disordered, as you'd expect. Solids everything has to have its right position. In a gas, it's mostly empty space, so that can be more. And so this is, what we have? We've got conflict again. One says go, the other says no go. And so we're stuck.
What is
Go means driving force is present. No go means no driving force. If no driving force, there should be no reaction. See, the problem is the types of reactions we were looking at in Chem 1A were reactions that we could kind of ignore this second thing and just look at the first one. But now we've got to consider a broader range of reactions. And so consider that. C, SO3, sulfur trioxide gas plus hydrogen gas yields sulfur dioxide gas plus water, H2O, in gaseous state. What do you think is happening with delta H here? Would you say it's exothermic or endothermic, or maybe too difficult to tell?
Cannot
It's
tell.
gonna be exothermic
It's going to be exothermic. How did you figure that out, Adrian?
because it went from less stable to more stable.
And what clued you in? Does everybody see that? It should be exothermic? And what clues you in that it's probably more exothermic? The water, right? Probably the water would clue me in, because what would you rather have, water or hydrogen gas?
Water.
Yeah, for sure water, because hydrogen gas is not so stable, water. But then sulfur dioxide. But sulfur dioxide versus sulfur trioxide? I don't know. Which one's more stable? We could do it. You know what we could do? We could just draw out the Lewis structures and just estimate it based on bond energies. Right? But we don't have to. I think this is going to be exothermic. So this says driving force. And what's happening with the entropy? Entropy, you know, hydrogen's less complicated than water, but then sulfur trioxide is more complicated than sulfur dioxide. So I'd say it's pretty much a toss-up. And I'd say that the entropy is about 0. And so now we have a winner. We have a winner. This should be driving force. This one we can tell. There's going to be a driving force for this reaction. This is a redox reaction. So we're going from, stronger oxidizer, stronger reducer to weaker oxidizer, weaker reducer. Okay. So you get the point. The point is that if we do things qualitatively, sometimes we can tell. Sometimes both go one way. If you have both the energy and the entropy, if you have the energy decreasing and the entropy increasing, then it's perfect. You have a very strong driving force. Because if both of these say driving force, then the reaction should be quite favorable. But when we have a conflict, then it becomes quite difficult. And so the problem is we know how to measure delta H. Tell me all the ways you can determine what delta H is. Actually, take a minute and try to think back to Chem 1A and tell me all the ways you can think of to determine delta H. And I'll be right back.
That's what I did with
They have
That's what it is, equal. That's it. It's like, that's equal. That's why I said that's why it's
All right, how do we determine delta H?
By experiment.
By experiment? What kind of experiment can you do?
Calorimetry.
Which kind of calorimetry?
Calorimetry or?
Do we call it constant volume or constant pressure calorimetry? Constant pressure calorimetry will give us
Okay.
delta H. Yeah. How about constant volume calorimetry? That would be that would give us delta U, but if we got delta U, could we figure out delta H from delta U? Do you guys do you all remember how to determine delta H from delta U? You have to know how much work would have been done if you didn't do it in a bomb, right? And then compensate for that. And so there are lots of ways we can determine delta H. You know? And so let's try one right now for this. What would you say the easiest method to determine what delta H is? What would be the simplest? From chapter 7, your experience doing the homework problems in chapter 7, out of all those ways of determining what delta H is, what was the easiest? The Hess's law using adding up equations? Some people would disagree. I would disagree. I would think Hess's law is not the easiest using equations. Hess's law using delta H is a formation is by far the easiest. Do you remember that? And so most of the time in this chapter, that's what we'll probably try to do. We'll probably try to determine delta H for the reaction. This is equal to, it looks similar to the previous thing, but it's going to be the sum of mu P delta H of formation of the products, right, minus the sum of mu R delta H of formation of the reactants. You guys remember this equation? Products minus reactants. This is normally the way to see it, products minus reactants, except in that previous one. But we need to make sure we have the delta H of formation data in Appendix D. If we're lacking the delta H of formation data, but we could draw the Lewis structure, then we could use the previous equation I wrote on the board. But the previous equation I wrote on the board isn't so accurate. Why? Using the bond energies. The bond energies isn't going to be as accurate as this equation using Appendix D data because not because of entropy, because
The other one's based on observation. The appendix D.
Appendix D is based on observations, but also the bond energies are based on observation. Why did I, earlier I wrote, which is approximately equal to the sum of the bond energies of the reactants minus the sum of the bond energies of the products. Why did I write approximately equal to? Why didn't I just write equals to? Individual bond energy, yeah. There's something that's on the right track. Individual versus what? We're doing the whole molecule because we're going to break apart the whole molecule if we want and reform them.
Because some work down to do the rearrange the octal.
Actually, no. Kind of. Well, what it is very simple. The table of bond energies are accurate and precise. Our bond energies, like for example, when I break, this is the example given in chapter 7. If I break this first one, it costs me X kilojoules per mole. The second one cost me exactly the same? No. And so the table of bond energies is called the average bond energy. And what is the spread? The spread of bond energies is quite wide, yeah, broad. And so we're just using these averages. The averages always run the risk, that's not entirely accurate, because we're dealing with our specific bonds. The specific bonds might not have that average energy. That's the problem. So what you should do is you should go back and review chapter 7. And so, and also some other stuff too. For example, let's say I have gas A in this container here. So this is gas A. And then over here I'm going to have gas B. We're going to say these are ideal gases. And so I should add that on here. Ideal gas A, ideal gas B. And I have it separated by a valve here. And this is going to be at 298. Why 298? Yeah, that's our room temperature. And another reason why 298 is because Appendix D is at 298. Most of our thermodynamic data is at 298. And so if I open the valve and then let them mix, and so the gas A is going to spread into the other container, and the gas B will do the same, and pretty soon we'll have this mixture of gases, right? It's going to be at 298. Would you say that this process is spontaneous? Yeah, this spontaneous is a driving force. This is going to happen. If you open the valve, two gases are going to mix like that. Tell me what happened to delta H. Delta H stayed the same? Yeah, was work done? Sometimes work can be done, but you don't notice it because of this. If you have a gas that's trapped in, let's say, a small container here, and then we open up this valve. If we open up this valve and let this gas expand, then what happened to the system? The system originally was this. Now the system's grown bigger, so the volume changed, and work is P delta V. So it looks like work was done. But if we open the valve, there are two ways we could do this. Do you guys remember isothermal and adiabatic? Isothermal and adiabatic. Those were discussed in the homework more than in the chapter. There are a couple of homework problems in chapter 7 that deal with isothermal versus adiabatic. Isothermal, if we do this isothermally, then the temperature at the end of this will be the same. If we do this adiabatically, the temperature actually goes down because work was done. The energy came from the strain. But anyway, we'll just forget about that, and let's look at this. This is at 298, this is at 298. What happened to the energy? Maybe thinking in terms of delta H is difficult. maybe we should think in terms of delta U, because sometimes delta U might be easier to relate. You know, because especially since we know the relationship between delta H and delta U. And so if I think about this, what is U initial here? Tell me what U is again. U is, I know this is hard to remember,
Total energy.
the total energy. And the total energy is equal to the total energy equals what plus what? Oh, there's lots of ways of saying it. This is what makes thermodynamics tricky, because yeah, the total energy is equal to the. Is it really Q plus W?
It's a stable shoot, so only relate to the temperature, right?
You have to be careful because delta U. I know delta U. Delta U is equal to Q plus W. First law of thermodynamics. But is U equal to Q plus W? No. What is U equal to?
Something related to the temperature.
Yeah, you're right. It is temperature only. It's U, the total energy, is equal to the kinetic energy
Oh,
plus the
potential.
potential energy.
Which is really fast.
And so this would be the initial kinetic energy, this would be the initial potential energy. U final will equal the kinetic energy final plus the potential energy final. Right? This is what makes thermo difficult, because you have to remember all these. And the problem is you quickly forget them, but you need them for the next little segment of thermodynamics, which is this chapter. And so think about the difference. Think about the student who has all these down. You know, they're ingrained in that student's memory, versus the student who doesn't have any of these memorized. You know, they're going to have a huge advantage over you if you don't have these where you can come up with them right away. But anyway, what do we know about the potential energy of ideal gases? Keith? Zero. Yeah, the potential energy for ideal gases is zero. Ideal gases have no potential energy, right? They're only kinetic energy, and so you're right. They only depend on temperature, because kinetic energies and temperature are directly proportional. And so here, did the temperature change? No. Therefore, delta U will equal zero. You know, the energy before was the same as the energy after. And so here, that means delta H will equal zero. And what happened? What's driving this then? There's no change in energy. What's driving this is a change in entropy. And so here we can see that entropy goes up. And so one thing you want to do for this chapter is make sure you go back and review all these from chapter 7. And now we're going to add a new one. The new one we're going to add is entropy. And we want to figure out all the ways to determine entropy, just like we figured out all the ways to determine enthalpy. You know, but first we need to know the definition. You know, kind of what is the definition of enthalpy? H. H is defined, you know, we know the definition of H. H is defined as U plus PV. What does that mean? Can you know, lots of people can memorize that, but the thing is, you don't want to just memorize, you want to put it in your own words. So what was your little story that you associated with this? Did you have a little story associated with this? You know? And then we know that delta H, right, delta H is equal to delta U plus P delta B, etc. And so the thing that will help you with thermodynamics is just not memorizing this, but memorizing it and then trying to associate, some kind of mental picture with it. For example, why, well, enthalpy and internal energy are the same. They're energy, but enthalpy also has the pressure volume state. Why? Somebody asks you, why is pressure volume in here in addition to the internal energy? Isn't the internal energy the total energy?
That's where it is.
And so this is a thermodynamics question, exam question. Thermodynamics exam question. Why is pressure volume? I thought total energy was U. Why do we have to consider anything else? And then you would have to answer. What?
Like for gas work. Work done.
Yeah, work. I mean, this would be how we talked about this earlier in Chem 1A, but we talked about the surroundings. This would be the internal energy of the system. We got to see how the surroundings, either expansion of the system or contraction of the system will interact with the surroundings in terms of energy. So we talked about that. So we'll need the pressure volume state to see about that. So you come up with little stories to help you remember these things. That's very helpful. And, good. And so what about entropy? Entropy is a lot less, maybe it's a lot easier to deal with, because if we look at the Boltzmann equation, we'll see that the entropy is just given as this. Entropy is equal to K ln W. K ln W. Actually, let me see if I'm going in order here. Yeah, I'm going here.
Is that
So-
natural law? Is that natural law?
Yeah, natural law. K is called the Boltzmann constant. Boltzmann's constant is the same thing as the ideal gas law constant, except rather than per mole, it has different units. We'll look at it in more detail later, not right now. This is natural law. W is the ways, number of ways to arrange the system. So we'll call this S of the system. If there's only one way to arrange the system, then W is 1, and the natural log of 1 is 0. And so the entropy is 0. If there's only one way of arranging the system, then what we can say is perfectly ordered, And this would be like a crystal, a perfect crystal. A perfect crystal would have each atom or each ion or whatever, each molecule in the exact right position, and that's it. There's only one way. You couldn't even have vibrations, because if you have vibrations in the crystal, then there are more ways to arrange the positions of the atoms. And so this crystal has to be frozen, and so everything's just in its proper place, because once you start warming it up and adding kinetic energies, then there are more ways. In other words, there are more positions those can occupy. And we have this kind of thing. And so that seems simple enough. So if I take a mole of water, how many ways are there to arrange a mole of water molecules in 18 milliliters? It seemed like asking. Do you want to count them? Because not only do you have to count them, you have to think, oh, this is at 25 degrees C, so you have vibrations, you have rotations, and you have translations. And so you got to freeze it and then see, the positions of those. And so we aren't going to be doing any Boltzmann equation calculations, unless it's very simple, like one way, 2 ways, 2 ways, 3 ways. And so let's figure out. The Boltzmann constant is just, if we want to calculate, it's just R divided by n sub A. And so rather than R is in per mole, so it'd be 8.314 joules per mole. Actually, we could just calculate it. 8.3145 joules per mole Kelvin. And n sub A is Avogadro's number, 6.022 times 10 to the 23rd moles. And so the moles cancel, and that gives us units of joules per Kelvin. And so entropies are in terms of joules per Kelvin unit. One of the things that entropy is related to is heat. And so this one we aren't going to use much, but this one we probably use a little bit more. And so alternatively, use this one. This is not the Boltzmann equation, but delta S is equal to Q reversible over T. And where we can use this is in particular phase changes, etc. And so if we use this for phase change, then we think about this. If we start off with a solid, and then we convert that solid to a liquid, what's going to be one way we can convert a solid into a liquid? We add heat, right? As we add heat, and the more heat we add, perhaps the more disordered the system becomes. And so when we're thinking about this, then as we think about Q reversible, well, Q reversible, this is kind of the solid liquid equilibrium. Q reversible here would just be delta H of fusion, the amount of heat under what conditions? Under what conditions is Q equal to delta H? Under what conditions is Q equal to delta H? A, constant volume conditions. B, constant pressure conditions. C, all conditions. Constant volume conditions. Although volume doesn't, is it? Q, in other words, is delta H equal to Q sub V or Q sub P?
Q sub V.
Q sub P. Delta H is equal to Q sub P. Sometimes Q sub P and Q sub V are the same. When? Are QP and QV the same? When the system undergoes no volume change, either a constant pressure or constant volume, right? The whole point of this is to try to confuse you so that it gives you some motivation to review this stuff so you don't get confused, right? Anyway, this so delta H of fusion in the forward, and then we have delta H what we call freezing or crystallization or whatever in the reverse fusion. And so if we want to calculate the delta H of the, delta S of the phase change, for example, it might be something like delta H of fusion divided by the melting point temperature. And so the more heat that was required to melt this at this given temperature, the bigger the entropy change should be. Or, it could equal delta H of freezing at the freezing point. The freezing point and the melting point should be the same number, etc. That's something we could add. But are we always dealing with a phase change? No, we're not. And so this equation has limited application in this form. Limited application in this form because we'd have to have a phase change, and so we could have vaporization, sublimation, condensation, deposition as the alternates here. But this equation plus the third law of thermodynamics can give us something very useful. And so if we look at delta S is equal to Q reversible over T and the third law of thermodynamics. We can get something very useful from this. What is the third law of thermodynamics? The third law just states this: the absolute entropy of a perfect crystal at 0 Kelvin is, so you have a perfect crystal, it's at 0 Kelvin, nothing's vibrating, nothing's moving, everything's in its proper place. How many ways are there to arrange a perfect crystal? Just one way, and therefore its entropy should be 0. That's the third law of thermodynamics. And so how is that going to help us with this particular equation? It doesn't look like it helps us much, right? But what it helps us deal with is, unlike internal energy, and enthalpy, absolute entropies can be determined. All right, what is an absolute entropy? When I use the word absolute, for example, what is absolute enthalpy, or what is absolute internal energy? Let's start off with absolute internal energy. What is absolute internal energy, and why can't it be determined?
Absolute is like all of it.
At any temperature.
Keeps changing.
It's not necessarily that it keeps changing. Absolute internal energy. First of all, do you guys know what I mean when I'm talking about absolute internal energy? It's not the absolute zero of energy. I'm talking about something different. When I say absolute internal energy, there are different ways we could calculate delta U. Delta U is just equal to U final minus U initial. We call this the change in internal energy. And what do we call the absolute? Yeah, the energy here, the final. Okay, so for example here, this is what I wrote in Chem 1A. We have methane, I think, and 2O2 gas. Maybe you could go back and look at the notes for this. We've got CO2 gas and 2 water liquids. I want to know what my absolute energy for this is. And so what is the absolute energy of 1 mole of methane and 2 moles of oxygen gas mixed at 298 Kelvin? It's too hard to determine. Why? Because of the potential energy. Good. The kinetic energy is easy. It's 298, but the potential energy is difficult. What makes the potential energy difficult? Yeah, it's the energy of the bonds and intermolecular forces and what they call the subatomic. What's holding the subatomic particles together? That kind of stuff. So this is the the absolute energy of this is just like this. I have water. I have this water sitting at 298 Kelvin. Tell me what its energy is in kilojoules per mole. How many kilojoules per mole is this water? Well, you could calculate the kinetic energy based on the temperature. The temperature is close to 298, so we could calculate that. But what is the potential energy of the water? The absolute potential energy of the water. Well, but what you have to do, you break apart the water molecules, you break apart the hydrogens from the oxygens, and then you break apart the subatomic particles, and do those break apart? Is there potential energy stored in the subatomic particle? So if you have a quark or something, can that break apart into smaller pieces? Because if it can, then breaking costs you energy, forming releases energy, right? And so that's what we call, potential energy stored in those particles, because if you break it apart, it's going to cost you, and then reforming it, it's going to give you. And so we never determined these. Did you ever calculate delta U using this?
No.
Never, because we don't determine those, at least not accurately. They can be determined, but the error bars here are so huge that calculation becomes meaningless, right? Well, this is different, because do you know the easiest way to determine delta S? The easiest way to determine delta S is by just doing this, taking S final minus S initial. This is the way we're going to determine delta S the majority of times. Easiest method. So if somebody asks you what are all the ways to determine delta S, well, this has got to be by far the easiest. The absolute final entropy minus the absolute initial entropy. Well, then you go, okay, I know how to get absolute entropy. It's from the Boltzmann equation. I just need to know K, which is a constant, times ln W. I just count the number of waves. And so if I want to figure out what is my entropy of water here, I just have to figure out all the ways to arrange this, which is too much, right? Too much. And so how do I determine my absolute entropy here? Well, this is how I'm going to determine my absolute entropies. I'm going to look at delta S. Delta S is equal to S final minus S initial. And that's also going to equal Q reversible over T. We're going to look at small changes in heat, this Q. And so what we do is we use some calculus. And so we get this thing that says S final minus S initial. This is going to equal delta Q. Normally we don't use delta Q, right? Because Q is already delta. Q, if you have heat, it just doesn't sit there. Heat has to be transferred, from something with high kinetic energy to something with low kinetic energy. But in this case, we will. And then we're going to do something like this, and then if this delta is very small, this. And so what we do is we just take all this, and you don't have to pay any attention to this here. But basically, we can figure out what the final entropy is, because the final entropy is just going to equal this, plus the initial entropy. Well, if we say the initial entropy were 0 at 0 Kelvin, then we get an equation for this. And so the equation is going to look like this. When we're thinking about delta Q's, you've seen delta Q's before, or you've seen heat. Heat is going to be related to transfer of kinetic energy. Transfer of kinetic energy is related to heat capacity. Right? And so what we know here is eventually that the entropy, the absolute entropy, can be measured by measuring heat capacities in the end. Heat capacities, do you remember what the symbol we use for heat capacity? C. Good. We take C measurements, C, the heat capacity, etc. There's other stuff in here, so we'll just say ... but we don't care what it is. This is just heat capacity. And so the heat capacity is going to give us an indication of what the absolute entropy is. And so rather than figuring out all the ways to range these, I just measure the heat capacity of water at given temperatures. And so let's say I'm at 298 Kelvin. I measure the heat capacity. Is the heat capacity of water high or low, would you say? So the heat capacity of water is high. Why is it the heat capacity of water high? Because water can absorb a lot of heat, right, without its temperature increasing much. And so why can water absorb a lot of heat or a lot of energy? Why is it a good heat sink or an energy sink? It's a good heat sink or energy sink because there are a lot of ways that the water can absorb energy. It could cause vibrations, rotations, translations, right? And so water acts as a good heat. And therefore water is going to, if there are a lot of ways that water can absorb that energy, then there must be a lot of ways to arrange the system, which means the entropy must be fairly high in that sense. And so it's going to be related to that. Versus something with lower entropy would be like copper metal. Copper metal, you got copper atoms there. Are there a lot of ways to arrange the copper atoms? No, they're just going to vibrate. That's it. All right, we'll stop here and then we'll continue this next time.